So in the next part of the session, we're going to learn a bit more about how to draw and interpret the structures of organic compounds. So you're going to get a chance to draw some of these structures yourself and start to become the masters of compound structures. It might seem like they don't mean a lot yet, but I'll show you that you can actually work out quite a lot about a compound just from its structure and the way it's bonded. And that's where we're going to lean on what we did in the first part of the session, where I showed you how and why all the atoms come together to form these compounds. Now we're going to actually put this into practice by drawing some compounds and the different ways you can represent them and work out some of the different characteristics they have. So there are different ways we can represent organic compounds. So what we've looked at so far in terms of showing the bonds between atoms, we call that the complete structural formula. So there are some more simplified versions that we can have a look at that sometimes will give you less information but be quicker to write. So we need to be able to interchange between these different ways of writing the structures and drawing the structures and interpret what they actually mean. So you're going to see each of these different representations in the course, and we need to be able to actually know what each means. So the simplest one is called the molecular formula. So this is where it just tells you the number of each type of atom present in the compound, but unfortunately it doesn't give you any information about how the atoms are actually arranged in that compound. So the amount of information you're getting from the molecular formula is actually quite limited. So let's have a look at a molecular formula. So here's C3H8. So it's telling us that there's carbon atoms, hydrogen atoms, but if you don't know anything about the way that carbon and hydrogen bond, you wouldn't actually know what the structure looks like at all. So let's look at what the C3H8 does and doesn't tell us. Well, first of all, it tells us that there's 3 carbon atoms because there's a 3 after the C here, and it also tells us that there's 8 hydrogen atoms. However, it doesn't tell us how the carbon atom and hydrogen atoms are actually arranged in the compound. So if you didn't know that carbon forms 4 bonds and hydrogen forms 1, you would have no idea about how the compound would actually look if you drew it out fully. So based on our knowledge, we could actually use the information that carbon has 3 atoms there and hydrogen has 8 and try and draw a structure that actually fits that. And we'll see in other representations that it gives us a little bit more information to help us with this. So the complete structural formula is the one we've sort of seen so far in this session when I've said it's been the simplified representation. This one actually shows every single covalent bond within the atom, and it's showing that as a line. So it actually gives you a lot of information about how the different atoms are arranged in the compound. So let's look at the same structure. So remember in the molecular formula it was C3H8, but this time we've got the structural formula. It's still got 3 carbon atoms and 8 hydrogens, but now we can see the covalent bonds between each of the atoms. So it's giving us a lot more information about what the compound is and how it's going to behave. So it tells us that there's 3 carbons, 8 hydrogens, and it's giving comprehensive information about the bonding of the compound. So when you draw compounds out, usually we'll put it in this form, but there is another simplified form that we commonly see it in, and that's what I'm going to show you in the next slide. So we call this the condensed structural formula. It's kind of a modified version of this complete structural formula. It shows you the structural formula as text. So we remove some of the bonding. The only bonds that we see is the bonds between the carbon atoms. So I'll show you what I mean by this. So the same structures we saw in the previous slide can be represented as CH3, CH2, and then another CH3. So you might sometimes see this written as CH3 line, which represents a bond to the next carbon, CH2, and then another line to CH3. So either of these representations is acceptable. So when you see CH3, CH2, CH3 in a line like this, what that actually means is you've got carbons linked together. And the hydrogens that come after that carbon is just telling you the number of bonds to each of the carbons there, between the carbon and the hydrogen, I mean. So again, this condensed structural formula tells you that there's 3 carbon atoms, 8 hydrogen atoms, and now it is giving you some information about how the atoms are arranged, but we need to be able to interpret what these CH2s and CH3s mean, and the fact that drawing it in this form is dictating that we've got this arrangement of carbon atoms in a row like this. So in this representation down here, you can see how you can interchange between 2 of the types of formula I've shown you. So at the top here we've got the complete structural formula, and we've got the condensed structural formula down the bottom here as well. They're exactly the same structure, it's just 2 different ways of representing the structure. So essentially the CH3 matches to part of this structure, as with the CH2 and CH3 here as well. So you can see that the first carbon there has 3 hydrogens attached. It's the red one there with the red circle around it. So that corresponds to a CH3, which is here. So the CH3 means we've got 1 carbon atom and then 3 bonds to 3 separate hydrogens. Next, in the middle, is our carbon that has 2 hydrogens attached. It has only 2 hydrogens attached because its other bonds, here and here, are to other carbon atoms. So remember, each carbon needs 4 covalent bonds. So again, that will have 4. And then the last one at the end here is another CH3. So although it looks like we don't have a lot of information from the CH3, CH2, representation, it's actually exactly the same as drawing this whole structure out here. It's just a different way of representing it. So this representation of putting the carbon atoms associated with their hydrogens in this condensed form is something we're going to see quite a lot of in this course. So make sure that you realize that CH3 means that we've got a carbon atom bonded to 3 hydrogens. Whereas if we have a CH2, that means we've got the carbon atom bonded to 2 hydrogens. What it doesn't show you in this condensed form is the bonds between the carbons. So you just have to know that there's a bond being formed between these 2 carbons and another bond formed between those 2 carbons, because we've got that chain of carbons in that way. So the last form that we can represent a organic compound in is called the line bonding formula. So this is an even more simplified way of drawing these structures, where a line, the end of each line is the position of a carbon atom. So essentially what the lines are representing are actually the bonds between different carbon atoms. So this is most commonly used for hydrocarbon compounds that only contain carbon and hydrogen, but it can be used with other atom types as well. For example, if there was an oxygen in there or a fluorine, then you would have a line that shows that atom type at the end there. So I'll show you that in a little while. So again, we can interchange between these different representations that I've shown you. So the previous one was the condensed structural formula, where we had the CH3, CH2, CH3. And this actually simplifies down to the line bonding formula here, where we've got the lines in this triangular arrangement. So remember, based on the description here, there's actually a carbon atom at the point of each line here. So drawing the triangle shape here is you've got one line here and then another line there. So at the end of each line there, or the point of each line there, we've got a carbon atom. As well as there being carbon, we've got the associated hydrogens as well, but we don't draw those in for this line bonding formula representation. So what does the line bonding formula actually show you? Well, it shows you the chemical bonds between the carbon atoms within the compound, but not the hydrogens. So the amount of information you're getting from the line bonding formula is a little bit limited. It is most commonly used when you've got a really long structure. So for example, the line bonding formula, like this, could be used to represent a really long hydrocarbon structure that's made up of lots of different carbons. So remember, at each point on the line, at the end of a line here, we've got a carbon atom. So that would correspond to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 carbon atoms within that line bonding formula there. So let's see how we can interchange between the complete formula, where we've got the structural formula showing all of the covalent bonds, and turning that into a line bonding formula. So let's do the one on the left hand side first. So the first bond between the carbons there, it's shown in red, becomes the first line. We've only got one other bond between the carbons there, so that means we've got that second line there. So essentially, in the line bonding formula, all you're doing is representing the carbons, but you don't actually have the carbons in the structure. So we just have to know that at the end of each line, or the point of each line, is a carbon atom. So this is equivalent to having one carbon there, one carbon at the top, and then a carbon down the bottom here. What about though if we have an atom type other than just carbon and hydrogen? Remember, the hydrogens aren't shown, but what about something like fluorine? Well, we still represent the carbon atoms as single lines, so we'll bring those down again like that. But what about fluorine? Well, we need another line there to represent fluorine, and we also need to show the F, because if we didn't show the F, it would just be presumed that it was another carbon. So that's how we draw the line bonding formula if there is another atom type that's different to carbon. So here we can see 4 different ways of representing a hydrocarbon compound, which is also an organic compound. So each of these representations is the same compound. It's just 4 different ways of representing it. So up the top here, we've got the simple representation of the molecular formula, just simply showing the number of carbons and hydrogens present. Then to the right hand side here, the complete structural formula, where we've got the bonds between each atom shown. So something a little bit different about this compound is now we've got a double bond between these 2 carbons, represented by these blue lines here. So it's a bit different to the other structure I was showing you, because that only had single bonds. So this is going to affect the number of hydrogens present within the compound. I'll talk a little bit more about that later. So we can also represent this in the condensed structural formula, but notice this time that this one has less hydrogens associated with the first 2 carbons, and that is because the carbons have more bonds between the 2 carbons here, therefore they can't actually attach to as many hydrogens, because each carbon can only form 4 covalent bonds. So you can see here that the CH2 represents the first carbon in the structure, then the CH in the middle is the second, and we've also got a CH3 at the end here. So because the first 2 carbons here have less hydrogens than you might expect, that actually tells us that there has to be a double carbon-carbon bond between the first 2 carbons there. So we're going to practice looking for this in an exercise that's coming up. We can also represent the same structure in the line bonding formula. So just like the previous one, we take the bonds between the carbons and represent them as lines. So this one in blue is a double bond, so we do a double line for that. And then the second green line is coming from the second bond between the carbons there. So you can see the line bonding formula representation there as well. So remember, there would be a carbon at the end point of each line there, like this. So make sure you spend some time getting acquainted with each of these different structural representations, because they're really important to being able to understand and interpret, especially the organic chemistry part of the course, but also as we move into biochemistry, we'll see a lot of these types of structures. To understand it, it all comes back to the number of covalent bonds each atom type has to form, but then also just seeing the differences between these representations. And we will be interpreting it in all 4 of these representations. So we're going to do an exercise now where we need to try and interchange between these different structural representations that I've shown you. So this is something you can really only learn by doing. So I really do encourage you to pause the lecture at this point and have a go at this exercise. You need to practice drawing these compounds, and it will actually help you to remember how many bonds each type of atom forms and just get it really solidified in your head what you're actually learning. So I really do encourage you to have a go at this exercise. So for number 1 here, we've got a representation in the condensed structural formula. So the question asks us to draw the structure as a complete structural formula, so that's all the covalent bonds being shown, and also in the line bonding formula. So I'll give you a little bit of time to have a go at that now. Alright, so let's draw the complete structural formula first. So the first one here is a CH3. So that tells us that we've got 1 carbon atom bonded to 3 hydrogens, like this. So the next one is a CH2. So next to our CH3, we need to have a carbon that is bonded to 2 individual hydrogen atoms. So what's wrong with what I've drawn here? This carbon atom and this carbon atom both don't have 4 covalent bonds. Well, we need to make sure we're linking the carbons together because it's a continuous chain. It's one compound. So now that I've added that carbon-carbon bond in there, our first carbon has 4 covalent bonds, but the second one only has 3. So that means it's going to need to form another covalent bond. What will it covalent bond to? Well, it's going to covalent bond to the next carbon in the sequence, which is another CH2. So let's draw that in there. And the last one is a CH3. So let's draw that in as well. A carbon atom and 3 hydrogen atoms attached. So if you wanted to check that you were right, what you could do is you could count up the number of carbons and hydrogens in each of your structures. So let's do that. So we've got 1, 2, 3, 4 carbons. So carbon equals 4. And for hydrogen, we've got 3 plus 2, which is 5, and then 7 and 10. So we've got 10 hydrogens. So let's do the same over here. So we've got 1, 2, 3, 4 carbons. And how many hydrogens do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that's just a nice way of checking that we do have the correct structure. So we've been able to transfer from one structural form into another. What about the line bonding formula? So this one's a little bit trickier. So essentially we're just representing the carbon atoms as endpoints of the line. So we're going to take these 3 lines, and represent them in line bonding formula. So we're going to have one line to start with, then the next line. So that will, and then we need one more. So remember, the end point of each of these lines is a carbon atom. So drawing that, is equivalent to having the carbons at each end point of the line, like this. Alright, so we've got another one to have a go at here. So notice that the first 2 carbons here don't have many hydrogens attached. So that's a hint towards the fact that these carbons are going to have more than one carbon-carbon bond. So keep that in mind when you have a go at doing this part of the exercise. Okay, so the first one, we're going to draw the complete structural formula. So let's start with just drawing out what we have on the screen here, and then we can try and add the bonds where we need them to get up to the right number of bonds for each one. So initially we've got a CH, and then we've got a C, and then we've got a CH3. So now that we've got those individual pieces, let's try and make sure each atom involved has its right number of bonds. So remember, carbon forms 4 covalent bonds and hydrogen forms 1 covalent bond. So let's focus on the carbons first. So this carbon has 1, 2, 3 covalent bonds. So to get it up to 4, we're going to form one more bond to this carbon here. So now this carbon is good. We're happy there. Give that one a little tick. But these two carbons both lack 3 bonds. So this carbon has a single bond to this carbon, and this one has a single bond to the hydrogen. So how is it possible for these two carbon atoms to get 3 more bonds? Well, we can have a triple bond between the two carbons there. And that now means, if we count it up, this carbon has 1, 2, 3, 4 covalent bonds, and same with this one, 1, 2, 3, 4. So we can give each of those atoms a little tick. If we want to do our check again, we've got 3 carbons here, add up the hydrogens, 4. Do the same over here. So we've got 3 carbons, and then 1, 2, 3, 4 hydrogens. So it's a nice little way of checking that our structure is correct. What about the line bonding formula? So this is where we're just drawing the bonds between the carbons. So we've got a triple bond and then one single bond down here. So that's what the line bonding formula would look like for this one. So it's equivalent to drawing it like this with the carbons. But remember, to be completely correct, we draw it without the carbons, which is what I've shown you on this side. So this one, we're going to do it a little bit differently. So this time we're starting off with the line bonding formula, and we need to change this into 2 forms, the complete structural formula and also the condensed structural formula. So this one is a little bit trickier. So remember that at each endpoint of the line there's a carbon atom, so hopefully that'll help you get started. So give that one a go. So to start off with, it's probably worth just putting a carbon atom at each point of the line here, and that'll help us get started. So which one should we do first, the condensed structural formula or the complete structural formula? Let's do the complete structural formula first, might be a little bit easier. So let's draw our bonding out just with the carbons that we have here. So drawing in all the carbon-carbon bonding that we know from this line bonding representation. So this is equivalent to this. So when we have spare bonds missing, as we do here, we fill in the blanks with hydrogens because it's a hydrocarbon compound, which means it only contains carbon and hydrogen atoms. So let's add in the hydrogens. So for each carbon, we just need to work out how many extra bonds it needs to form. So let's go from left to right. So we've got our carbon here. It's already got 2 bonds. So how many more does it need? It needs 2. So let's add in another 2 bonds to hydrogen here. Second carbon, it's already got 1, 2, 3. So how many bonds do we need to make it up to 4? Just a single bond, which is a hydrogen there. And then these 2 carbons are both the same. They've got 2 bonds to other carbon atoms, meaning they need an extra 2 bonds to hydrogen. So those ones are the same. I've just added in those 2 hydrogens like so. And the last one at the end here only has 1 carbon-carbon bond. So how many bonds to hydrogen does it need? Well, it needs 3 bonds to make it up to 4. So there's our structure. So the last part of the question asked us to represent it as the condensed structural formula. So remember, that's where we've got the CH3, CH2, etc. So all we have to do is count the number of carbons, the number of hydrogens attached to each carbon. So we start with the one on the left here, that's a CH2. So we write CH2. The next one is a CH, so that'll be CH. And then we've got CH2, CH2. So we'll put in two CH2s. CH2, CH2. And the last one is a CH3. So we've now drawn both representations. So you can see how from something as simple as a line bonding formula, we can actually work out what the entire structure looks like and also change it into this condensed form, all from the knowledge that carbon has to form 4 covalent bonds and hydrogen has to form 1 covalent bond.